Okay, so
Here I did this chemical reaction in terms of del S total, and I showed del S total was positive. Let's now do it the way you normally would in terms of delta G. I would say it's a reaction at constant temperature and at constant pressure, so I can use the special form of the second law that delta G is negative. So I calculate simply that delta G is equal to delta H minus T delta S. Delta H is 731.4 minus T. Delta H is minus 731.4. Okay, delta H is minus 70.
Minus 2 and 1.
Start again. Delta G is delta H minus T delta S. Delta H is minus 218.062 minus T times delta S is minus 98.7. So your entropy term is in fact positive, which mitigates against the reaction, but your enthalpy term is very, very negative, which mitigates in favor of the reaction. The delta G is negative, and so it's a spontaneous process. That's the way you normally do it. You do delta G, delta H minus T delta S, delta G is negative, and so it's a spontaneous reaction. And you can see, of course, that this equation is exactly the same as this equation divided, multiplied by minus T. Okay, so it's the same thing round, but now we're talking. But remember, this is the special case for constant T and P, and we generally, in everything we do, we try to arrange things in terms of constant T and P so we can use these equations. We'll talk a bit about this later. This isn't really a restriction, but realize that delta G is not always negative for a spontaneous process. Some people make that mistake, and then they get a little bit confused. It's a special case of the second law, but the one we use all the time. Okay. And once again, you see another way of looking at this. We talk here about it's a competition between the surroundings and the system. Okay, the delta S total, this can be negative as long as this is sufficiently positive, and vice versa. Here, it's a competition between H and S. H is the enthalpy change, but why is there an enthalpy change? H is the enthalpy, is the heat between the constant pressure. H is the heat transferred from the system to the surroundings. Why is there a transfer? Well, because there's a difference in bond energy. These have, PbO has stronger bonds than Pb plus oxygen. Okay, so the product here is more ordered. So in terms of simply order, the reactants are more stable. If PbO had the same energy, Pb plus 1/2 O2, it would fly apart, simply because the oxygen would go into the gas phase. Okay, it vibrates, the oxygen goes off. The entropy, just vibration entropy disorder favors dissociation. But the enthalpy, the energy, favors association because you've got stronger bonds here. So as you form the stronger bonds, heat is given off, goes to the surroundings. So you can look at this term here as the entropy change of the surroundings, which it really is, or you can look at it as the bond energy. So in this reaction, there's a competition. The strong bonds in PbO tend to favor the products. That's the delta H term, which is negative. The disorder favors the reactants because there's a gas there, and that is the delta S term. The delta S term is multiplied by T. So as you increase the temperature, the things vibrate more and more and more. This favors the thing flying apart. Okay, so if the temperature becomes high enough, the delta G will become positive, and the thing will be spontaneous the other way. At low delta G goes the other direction. At a certain temperature, the delta G would be 0, and the thing would be at equilibrium. Okay, so always a competition between the disorder of the system and the energy, internal energy of the system. It was the same thing in the example I gave you with the melting of a material. The melting of the material in the system itself, that's the entropy term, which favors, say, the gas over the liquid and favors the liquid over the gas. And then there's the enthalpy term. The enthalpy term indicates that although the solid is more ordered than, consider the solid to the liquid. If we consider a solid going to a liquid, the delta G is equal to delta H minus T delta S. So for a solid going to a liquid, the delta S term is negative. Oh, sorry, the delta S term is positive, because the liquid is more stable than the, it's more disordered than the solid. Okay, but the delta H term, in going from the solid to the liquid, is negative because the solid has stronger bonds in it. The bonds are stronger. So the bond energy favors the solid, the negative term here. Okay, the disorder favors the liquid. Okay, so this term is negative, and this term, including the minus sign, is positive. Okay, so the solid is favored because it has stronger bonds than the liquid. The atoms are lined up closer together, more near its neighbors. The liquid is favored because it's more disordered. As the solid vibrates more and more, it's more tendency for it to form a disordered liquid. Okay, and that's why there's a temperature term here. So at high temperature, this term wins, and the liquid is stable. At low temperature, this term wins, and the solid is stable. At exactly the melting point, the two terms are equal, and delta G is 0. So the equilibrium T-naught fusion would be the equilibrium melting point. At the equilibrium melting point, delta G is 0, and at the equilibrium T-fusion, at the equilibrium melting point, delta S, the melting entropy, is equal to the melting enthalpy divided by. Okay, so the entropy of fusion of water is equal to the heat of fusion of water divided by 273.15. This equation, delta S is delta H over T, only applies at the equilibrium conditions. Okay, because it's only at the equilibrium conditions that delta G is 0. I have seen people apply this equation elsewhere. It's not true. Okay, so again, competition between the bond energy, which favors the solid, disordered, which favors the liquid, or if you had liquid gas, it's the same thing. Disorder favors the gas. Bond energy favors the liquid. And these are related to the entropy change of the surroundings. That's how it's all goes together. Okay, I just wanted to do, this is kind of theoretical stuff. Let's, this is more or less a rigorous way of doing it, the modern way of doing the second law. But you might be interested, because you've seen this in books, is probably the way you learn thermodynamics. As an undergraduate is looking at Carnot cycles and all this kind of stuff, and this is the way Clausius and the guys did it back 170 years ago. And what the hell, I think let's just do it because it's interesting to see how it works. Anyway, Clausius and people back then, this was during the Industrial Revolution in Britain, and people were trying to understand heat engines, steam engines and things. And they were trying to understand how these things work, what equations you could use for them. They observed that, first of all, that you cannot convert heat entirely into work, which is what a heat engine you're trying to do. You're trying to heat the thing up, you're trying to burn something and turn it into work. And they determined that you just couldn't get all the heat energy would not be converted to work. Only the free energy could be converted to work. There was a certain part of the energy that somehow seemed to be not free. It was bound up somehow. Of course, we don't know that's the T delta S term. Okay, so why can't you convert heat? You can convert work entirely into heat. You just whack something and everything's heat, but you can't convert heat entirely into work. You can only do it partially. And they're trying to understand how these things worked, and they were interested in what they call a heat engine. A heat engine is a machine to convert work into heat by going through cycles. Okay, so I'm going to go through this quickly, not rigorously, but just to show you, in case you saw this before, how does it work? Consider a Carnot cycle. So they call this the Carnot cycle. I did a cycle in the problems number 1-4. Carnot cycle, you imagine this is a system in the old piston thing again. Here's your system down here, and this is pressure and volume of the system, and the thing's going up and down and doing work and exchanging heat and work with the surroundings and so on. I'm doing this quickly. You're not responsible for this. I'm just trying to give you the flavor. The Carnot cycle, you can have various cycles. I think the one I did in the 1-4, you had a constant volume process and an adiabatic. Okay, but what we're going to do here, we're going to start at some initial state, and we're going to have a T1 is constant. So we're going to have an ideal gas. So inside of this thing, we're going to put an ideal gas. Well, you can find this in any book on thermodynamics. And we go from an initial state 1 to a final state 2 in this direction at constant temperature. So this is an expansion step, so you're doing work. And let's do it reversibly. Okay, so we do it reversibly, and this the integral under this area here, PDV, is the amount of work that you get out of the system. All right. And you got to supply heat. So up here, Q1 is positive, and W1 is positive, because maybe I should use a 1 like this. Okay, Q1 is positive and W1 is positive. It's doing work. Sorry, W1 is negative. It's doing work, and you're adding heat to the system. So here you're heating the thing up. This is the high temperature step. You're burning your fuel, you're heating the system up, and it's expanding. This is the power stroke. Then we have an adiabatic, Q equals 0, an adiabatic expansion. So we consider the thing to expand a little bit more, but it's now insulated. So it does a bit more work, okay, but the temperature drops. Okay, because the internal energy is being used to do the work. Okay, that's also a bit of a power stroke. Now then, we then have to go back, we have to put the system back where it started from. So we do another thing at T2, which is constant. And here we have Q2 now is a negative, and Q1 is, W2 is positive. So now we're going this way. Now we're pushing the thing down, we're doing work on the system, and heat's being given off. And T2 is less than T1, of course. And now we reach another point here. We'll call this point 3, we'll call this point 4. And now we do an adiabatic expansion, adiabatic compression, Q is 0, in order to put the thing back up where we started from. All right. Okay, so we're going around a cycle, and after we're done, this is the amount of work that the system did on this stroke. This is the amount of work the system transferred to the surroundings. Here we had to put work back into the system, so the work we had to put back into the system to compress it is equal to this integral under here. And the total work, okay, W net, is the area inside the figure. And that's negative, so the system has done some work. Is that clear then? Okay. We do 2 expansions, we do 2 compressions. The work of expansion is the integral under this curve. The work of compression is, which is positive, is the integral under this curve. The total work you get out of the system is the area inside the figure. And the same thing now, delta U total, which is the integral around the closed path. We go right around the closed path, and delta U total is 0. That's actually nothing to do with an ideal gas. If you're taking the system back to where it starts from, the total internal energy change is 0. Okay, so U is 0, so that's equal to Q total plus W total. Okay, so obviously Q total then is the total area, again, inside the curve is the total heat. Okay, so this is the total work, which is negative. The system's done a net amount of work, and you put a net amount of heat into the system in order to do the work. So you heated the system up. Here you put heat in, here you get heat back out, but there's a net amount of heat. Okay, and this is Q net, which is greater than 0. So you put amount of heat in, you put 100 joules in, you get 100 joules of heat in, you get 100 joules of work out. Okay, so it appears that you've converted heat completely into work, which goes against what I just said. What's wrong with this logic here? This is a heat engine. It's a device. In principle, you could build a Carnot cycle and you could run the thing. Okay, you would have to heat it, constant temperature. You'd have to then insulate the thing, let it expand a bit more. You'd have to take the insulation off, put it down to constant T, but you could do it. And you'd be converting heat into work, and this would be the net heat and the net work, and they're equal. So you've converted heat 100% into work. But you can't convert heat 100% into work. So what do they mean you can't convert? I mean, obviously, by the first law, energy is conserved, so the total heat's got to be equal to the total work if the total internal energy change is 0. The point is, it's the heat that you can, okay, this is the heat that you have to put into the system at high temperature. Here you get heat out, but it's at a lower temperature. This is the exhaust. You can't take the exhaust from your car, which is at a lower temperature than the cylinder, the energy, the heat in the cylinder, and somehow take that heat, heat it up, use that heat to go up to a higher temperature and run the next cycle. That's lost heat. Okay, the low temperature heat is lost. You cannot take that heat and heat it up again. You can't take the heat and pump it uphill to a higher temperature. It's lost. You can't use it again. It's not usable. Okay, the total work, however, unfortunately, this is the total work you do, and then you really do have to compress the thing and put the work back in. So the net work is really area inside the curve. But the total heat that you got to put in is just this area during the two expansions. That's the heat. You put in heat during heat during this expansion. The heat that you get back, this heat that you get back here is just lost. Okay, so the efficiency then really is equal to the work that you get, which is this area, divided by the heat you put in at the high temperature, which is this entire area, and that's less than 1. So your heat is not being, you're converting some heat into work, the rest of the heat you're lowering, the temperature's dropping. You can't do anything about it. So that's what they mean by the efficiency of the engine. Clearly the difference between the two temperatures, you've increased your efficiency. That's why if you can run the higher the temperature you can run your engine, the more efficient it is. If you could run T2 at 0 Kelvin, then you would have 100% efficiency. Okay, so this tells you immediately then that the higher temperature, the higher you can make the engine, the hotter you can make the engine, the more efficient it's going to be. So there's your heat engine. Suppose you run a heat engine the other way around, what are you doing? If you run so this is your heat engine, this is the work you get, this is the energy you put into it. If you run the thing the other way around and it goes the other way, you're putting work in. This is the amount of work, the net amount. Now if you run the thing the other way, you just go around the cycle counterclockwise. Okay, the net amount of work now you're putting into the system is this. Q2 is now positive and Q1 is negative. So what's happening here is that you're pumping heat from the low temperature to the high temperature. You're taking energy, you're putting energy in, heat is being absorbed here, and it's being, I've got this back in. Q1 is negative, and Q1 is positive, you're adding heat to the system. I don't always get confused with this. If you go the other way around, what am I doing wrong? One is negative, right? I guess those doing work. Q1, that must be positive. Why? Maybe I should quit for the day, huh? Q1 is positive. So you're adding heat to the system. And it's doing work. Oh yeah, of course. Jesus. If you run it around the other way, if you run it the other way, Q2 is positive. So what's happening is the system is absorbing work at the low temperature, heat at the low temperature. Q1 is negative, so it's giving off heat at the high temperature. So it's a heat pump, a refrigerator. You're putting energy into the system. This is the inside of the refrigerator. This is the outside world. You're pumping heat from low temperature up to high temperature. We're removing heat from the inside of the refrigerator. You're putting it out into the radiator on the outside of the refrigerator. So it's a heat pump. You put in this amount of energy and you get out a certain amount of heat. And you pump up a certain amount of heat, so it becomes a heat pump. So you're pumping heat uphill. Okay, so energy just flows spontaneously from high temperature to low temperature, but you can take heat from low temperature to high temperature if you put in work in order to go up. So you take this amount of heat in, you add an extra amount of work, and you get back up that amount of heat at the top. That's a refrigerator or an air conditioner or a heat pump. Okay, now the Carnot cycle is an ideal sort of thing, but I mean you could have other cycles. It doesn't have to be a Carnot cycle, your PV, you could be any sort of a curve like this, and you go around the cycle. You can draw the cycle for the Otto cycle for an internal combustion engine, you can draw the cycle for an idealized steam engine and so on, but it's still the same principle. You have a high temperature reservoir and a low temperature reservoir, which can sort of change temperatures, I suppose, a bit, but you end up with this is the total amount of work and you have the heat. Okay, so going around this way you get a heat engine, going around the other way you get a refrigerator. Okay, and this is the whole business about the efficiencies and so on. It can be reversible or irreversible. If it's irreversible, you get a lower efficiency than if it's reversible. Reversible will give you the highest efficiency for the particular thing. Okay. So how does this relate then back to the whole entropy affair? Without going into every detail. This is an ideal gas. Okay, let's say it's an ideal gas. Temperature is constant up here, so remember that Q is then equal to minus W. So we'll take 1 mole of an ideal gas. So Q up here, if I'm not making a mistake, is minus R log V2 over V1 times T. Q is minus RT log V2 over V1. The work of expansion will be greater than RT log V2 over V1. The Q is minus nRT log V2 over V1. Okay. The Q down here, the Q2 then is equal to plus RT log V4 over V3. If you work out the ideal gas law. If you look in your textbooks, you'll see that for an ideal gas, an adiabatic expansion of an ideal gas, I'm not going to go through the mathematics, but the ideal, you have here, you have your constant temperature, then you have an adiabatic path, then you have constant temperature and adiabatic path. You can show for the Carnot cycle that V2 over V1 equals V3 over V4. That can be shown from the properties of an ideal gas. Okay, and so what you basically end up then is you end up with Q1 over T1 equals minus Q2 over T2. Q1 over T1 equals minus Q2 over T2. Okay, but this is delta S of 1. This is delta S1, and this is delta S2 by our definition of Q reversible over T. Okay, so delta S total is 0 for this reversible heat engine. Delta S total is 0. Okay, therefore he is showing, okay, this is why the whole thing's confusing when you present it in this way, but I'm just trying to show you how, now that I've presented it in the modern way, this is the reasoning that Carnot and the guys went through. For an ideal gas going around a cycle, Q1 over T1 is minus Q2 over T2 if it's reversible. So if we talk about entropy as Q reversible over T, the total entropy change will be 0. What does this mean? This means it's possible to, but what is T? Okay, T is your arbitrary idea of what temperature is. So the right way to say this is it is possible to define a temperature scale such that Q1 over T1 is minus Q2 over T2, or we will define the temperature scale such that Q1 over T1 is equal to Q2 over T2 for any Carnot cycle for an ideal gas. Okay, so we can define, the temperature scale can be defined in terms of the Carnot cycle. In fact, that's how temperature is really defined. You can imagine you actually build a Carnot machine. You put the Carnot machine between 2 reservoirs, one at T2, which is, let's say, the melting point of ice. So this is at 0 Celsius, or this is at T1. Okay, you measure Q2, you measure Q1. Okay, T1 you set to be what you want, 273.15, and T2 you measure Q2, you measure Q1, and that tells you what T2 is. So this is a thermometer, a Carnot thermometer, and it's possible to define a temperature scale in such a way that the Q1 over T, the total entropy change will be 0. Okay, so you can use a Carnot thermometer, and that is in fact called the thermodynamic temperature scale based upon the Carnot cycle. Clearly this is not the best way to, easiest way practically to measure temperature. Now, so fine, that's for an ideal gas, but I'm going through this quickly. You can read your thermodynamics books after. I'm just trying to show you the reasoning. That's the, for an ideal gas, that's true. But let's suppose now, okay, you can look at this and think about it. You don't have to. I want to give you the spirit of the whole thing, but I don't think it's worthwhile spending like 2 hours going through it. All right, so now what he did is he's trying to show that the entropy, Q1 over, the entropy defined as dQ reversible over T is 0 if you have an ideal gas in your thing going reversible. And Carnot said, well, suppose you have any fluid. You're inside your piston, you don't have an ideal gas, you have anything. A non-ideal gas, a solid or a liquid or whatever, and it isn't even reversible. Then he's trying to show the same thing is true. Okay, that the ds dq reversible over t will still be 0. And the way he does this, I won't go through it, is he imagines two things. Here you have a machine, a heat engine, called X, and here you have a refrigerator called X prime. Okay, and what's happening is they're operating between two reservoirs, 1 and 2, at T2 and T1, which is the low temperature and the high temperature reservoir. These are two Carnot cycles. No, sorry, they're two Carnot cycles, but not necessarily an ideal gas. So in the reservoir, this is actually as a machine. So here you're adding heat in the high temperature reservoir up here, and you're removing heat in the low temperature reservoir. Meanwhile, the refrigerator is pumping heat from the low temperature reservoir up to the high temperature reservoir. And what's happening is here the machine is producing work, and the work is being used to run the refrigerator. And we assume the whole thing is 100% efficient, there's no friction losses and so on. Okay, so what he does is for each cycle then, del du is 0, so the work is QH over QL. You can read this through. Suppose that QH over T2 plus QL over T1 is equal to 0, but QH, so suppose that the heat engine, the machine, is, this applies, the equation applies that I showed, del S is 0, but for the refrigerator, which is another heat engine with another fluid, backwards heat engine with a different fluid, it's not the case. Okay, then you go through the entire cycle, and what you find is that QH is less than QH prime. And what this means is that heat is pumped spontaneously from reservoir 1 to reservoir 2. Think about, go through the logic here, and think about it. We're assuming now, I'm trying to show that no matter what the fluid is, this will always be the case. So let's suppose that this is the case. We've defined a temperature scale such that QH over T2 is QL over T1, but that's only true for an ideal gas. So suppose that the other one is not an ideal gas, and so this isn't true. If this is not true, and let's say arbitrarily we let flu low be less QL prime, then we end up with, we'll find that the thing runs spontaneously, and spontaneously pumps heat from low temperature to high temperature. There's no violation of the first law, because all the work from here is going over to here. The thing just goes round and round in circles, but what happens is heat's pumped from here spontaneously all by itself. Heat's moving uphill. Okay, and so then Carnot reasoned, well, we observe that heat does not, we observe there's such a thing as temperature. This is the basic physical observation behind the second law, that we observe that there is such a thing. We don't know what it is because he has no idea what heat is. Back then they had no idea that heat was the motion of molecules, but there is a form of energy called heat, which is not work, and there's a potential for this heat flow, which is called temperature, and heat always goes from the high to the low temperature. That's the only real physical observation. The rest is all logic. Okay, he did the logic with the Carnot cycle, with the ideal gas. Then he proves that no matter what the fluid is in the machine, it must be true that Q high over T2 plus Q low over T1 has to be equal to 0, or else you could pump heat uphill and heat could flow spontaneously from low to high temperature, which is not possible, not observed. Okay, then he says, okay, that's for a Carnot cycle. Let's say we have an arbitrary cycle, so then he takes your arbitrary cycle. How do I turn this around? You. He takes your arbitrary cycle and he shows that the arbitrary cycle can be divided into a whole bunch of little Carnot cycles. So there's your arbitrary cycle, but it can be divided into a Carnot cycle here, and a little Carnot cycle here, and a little Carnot cycle here, and you make them infinitely small. So you can show that any cycle is a sum of a whole bunch of Carnot cycles, and then he shows that no matter what the cycle is, QH over Q1 over T1, so therefore he shows that the integral of dq, therefore going through this whole argument, he shows that the integral around a closed path of dq reversible over t must be 0 for any fluid. Or, to put it correctly, it's possible to define a temperature scale such that for any fluid going through any cycle, dq reversible over t equals 0. Therefore, this must be the integral of a state property. Otherwise, it wouldn't be 0. You go back to the same state, you would have a change. Okay, if the integral of dq reversible over t is 0, this must be the difference of the state property. Therefore, there must be a property called S such that it's equal to dq reversible over T. Or it's possible to define a temperature scale based on the Carnot cycle such that for any fluid, for anything, the ds is equal to dq reversible over T. S must be a state property. Isn't that a beautiful bit of logic? He knows nothing about what heat is, nothing about the motion of molecules, only logic, and based upon the observation that there's something called heat, which is some sort of undirected form of energy, and that there's some sort of a potential called temperature for the flow of this heat. And from this you derive the fact that that there must be a state property S, such that ds is equal to dq reversible over T for any process. Okay, that is a perfectly rigorous derivation of the second law, with no recourse to discussing what entropy and what heat really is, that entropy is disorder, no idea, but it's got to exist. This, by the way, only defines ds, not S absolute. So here you really need the third law, that entropy of an absolute crystal at 0 degrees Kelvin is 0, which Clausius didn't need because he only cared about delta S and heat engines. But then when people with Boltzmann and the guys started to apply that, they had no idea what entropy was. I mean, back in the 19th century, if the student said, but what is entropy? It's a state property of a system, but what it is nobody really knew. Then they noticed for chemical reactions, by just looking at the delta S of chemical reactions, that S of an absolute zero of a crystal was in fact equal to 0. That you could only make sense if you postulated that, then all chemical reactions seem to fall into it. So that became a third law. And then Boltzmann started to think about what it really meant, and that sort of came into the modern entropy definition of entropy. So that's where the okay, then they also observed, okay, that's only the first half of the second law, is that there is a property called entropy where ds is dq reversible over T. It is a state property, which is the reason I went through here. Then the ds total must be greater than 0. It was again based on two things. It would show, I showed this where I did two things here where I had two systems in equilibrium at T1 and T2, and you could show that heat flows from high to low temperature, the delta S total was positive. Okay, so that showed the delta S total was positive. Then the other one was, if you have a reaction or whatever occurring at constant temperature, that the delta S was Q reversible over T minus Q irreversible over T. You know that Q irreversible is always greater than Q reversible, so delta S must be positive. Therefore, the total delta S must always be positive. So there is a property S defined this way, and delta S total must always be positive for any spontaneous process. And that was derived in like 1840 or something, with no recourse to anything else, and that's really absolutely remarkable that they came up with this whole thing. And it was only 50 years later that they actually kind of worked out what the whole thing meant in terms of statistics and entropy being disorder and so on. Now you can start the way I did, S is K log T, and I think that's a better way to understand it, because presenting it this way really, okay, but it makes you appreciate what it's all about and where it all came from and what the Carnot cycle is and all that kind of stuff. Okay, I'm going to stop. We'll talk next time. You can read a little bit on about temperature scales. So there is a temperature scale, and in principle then you build a Carnot cycle, and that's your thermometer, and you put that inside the room and you run the Carnot cycle, and that tells you what the temperature of the room is. There's got to be a better way than that. So we talk about the ideal thermodynamic temperature scale and then the actual practical international temperature scale, which we try to make as close as possible. One other thing to think about, 10 seconds, is Maxwell's demon. Have you heard about Maxwell's demon? Okay, Maxwell said here's the following. So you have here, say you have oxygen and nitrogen, and over here you have oxygen and nitrogen mixed. And here you have a little door, and you have a little gate. And here you have a little demon, a little devil. That's Maxwell's demon, okay? And what Maxwell's demon is he watches. And as he sees a nitrogen molecule coming this way, he opens the door and lets it through. Or if he sees an oxygen molecule coming this way, he opens the door and lets it through, but otherwise he closes the door. So eventually, by opening the door and observing the molecules, he can separate the gases. So then he has all nitrogen on this side and all oxygen on this side, so he has violated the second law of thermodynamics. So, what's the problem with that? And this actually led for 100 years, well, no, maybe not 150 years, to arguments by some of the top physicists and chemists about what's wrong with this. Why can't, how can Maxwell's demon, he observes a thing, so it had to do with, is it the observation of the molecules? No, they could be proven that that wasn't the case. Theologians came in and said this proves that intelligent beings have free will. You see, this is the difference between being and having a soul, and is that we as humans can actually violate the second law. The second law, okay, so this is this was a religious argument, and this was very important. Maxwell's demon, having intelligence, can actually violate the second law. That's not true either. He can't. Okay, so it sounds kind of silly, but I mean, there were hundreds of papers written on it. It was a real thing for 50 or 60 years. It was eventually solved only by Shannon in information theory in 1948, who had the definitive thing on the second law. Brion, of Brion zones, for a long time thought he had the answer, that it had to do with the entropy of observation, but then that was proven wrong. So anyway, think a little bit about Maxwell's demon, what the problem is here. He can't violate the second law, but why not? Because he seems to be able to.
Was there anything else I wanted to say?
Oh yeah, perpetual motion machines. A perpetual motion machine of the first kind is one that violates the first law. And these are the most common. You've seen perpetual motion machines where actually you're making energy. Your conservation of energy, you're getting energy from nothing. But there's perpetual motion machines of the second kind, which don't violate the first law, but they violate the second law. Why would it be wonderful if you could build a machine that violated the second law of thermodynamics? Why would that be a tremendous boon to mankind? What exactly does it mean? A perpetual motion machine of the second kind that violates the second law. One that you can pump temperature, you can pump heat uphill without having to put in any work. It doesn't violate the first law. I mean, if heat goes from low temperature to high temperature, no energy is created. You lose energy at low temperature, goes to high temperature. Design a wonderful machine that would solve all mankind's problems if you could do that. See, perpetual motion machine, they're more subtle. So most of the perpetual motion machines that are submitted to the patent office, who apparently will no longer look at a perpetual motion machine patent unless you have a working model. But most of them are of the second kind because that's much more subtle than the first kind. You can usually find a problem in the first kind, the second kind is a little more subtle. So design for me a perpetual motion machine of the second kind and show how it would work. Well, how it would work. If you could build it, why we wouldn't have to worry about, why that would solve the whole energy crisis. And tell me what's wrong with Maxwell's demon. Okay, and read the rest of whatever you want to read. Read the rest of the chapter on thermodynamics. Actually, chapter 4 going into the, I don't have an index in this. Actually, the first part of chapter 4, which is the rest of chapter 2, you can look at chapter 3 with the phase rule. And chapter 4 up to the part on phase diagrams. 4.1, section 4.1. So the rest of section 2, section 3, and 4.1. Let's say the order would be the rest of section 2, 4.1, and then 3 to read. No, I'll give you the homework problems on Thursday. Okay, thank you for your attention. That went longer than usual. I'll try to be shorter on Thursday. Okay, now we have to do this, right? 1, 2, 3, go.